Hello everyone, thanks for coming. So today we're going to do a review of our week 4th lecture of our numerical analysis class. So first, we talk about doing pivoting to get the pivoted LU factorization of a matrix. We introduce the concept of a permutation matrix. So permutation matrix is a matrix in which is a square matrix in which every element is either 0 or 1, and there is exactly one non-zero element in each row and each column. So basically, if I apply the permutation matrix to another matrix by doing the matrix product, the permutation matrix will shift the rows or columns of another matrix. So there are some basic properties of the permutation matrix. Every permutation matrix can be obtained by permuting the identity matrix I, and if there are two permutation matrices, then their product is also a permutation matrix. Also, a permutation matrix can be written as a product of basic permutation matrix. That is to say, by only permuting two rows of the identity matrix, which we will call it as a basic permutation matrix. So if we write a permutation matrix as a product of several basic permutation matrices, the determinant of the permutation matrix is only determined by the number of basic permutation matrices in this product, because the determinant of each basic permutation matrix is -1. So with the permutation matrix, we can do the pivoted LU factorization. There always exists a permutation matrix P, a unit lower triangular matrix L, and an upper triangular matrix U, such that PA equals to LU for a square matrix A. So here we don't require that each leading principal submatrix of A is non-singular. Here we don't have any restriction on the matrix A. If A is singular, then U is singular, but L should be a lower triangular matrix. So finally, we formally introduce the concept of computational cost. Note that we can always use these two formulas to calculate the elements in the LU factorization of our matrix A. So using those two formulas, we can also calculate the total number of additions, subtractions, multiplications, and divisions needed. For calculating each Lij, the total number of operations needed will be 2j minus 2. On the other hand, when we are calculating Uij, the number of operations needed will be 2i will be 2. For 2 Lij, the total number of operations needed will be 2j minus 1, while for Uij, the total number of operations needed will be 2i minus 2. Note, here we always start from the first row of the lower and upper triangular matrix U, and then the first column of L, and then the second row of U, and then the second column of L. We proceed until we calculate all rows of U and all columns of L. So basically, for an n by n matrix vector equation, operations needed to calculate the LU factorization will be around 2 over 3 n cubic. The operations needed to calculate an upper or lower diagonal system will be around n squared. So we can see that the operations needed to calculate the LU factorization will dominate, and the overall cost for using the Gauss elimination or using the LU factorization to solve a matrix vector equation will be big O cubic. So compared to other methods, LU factorization will be very computationally expensive. However, it is still the most basic method to do the matrix vector equation. Thanks for listening.